present the result of a common lab we have started with a research center in France called the CEA List. You might have probably heard of. The CEA List and PragmaDev have created this common lab called PragmaList. And just a few words on the company, you briefly introduced. We come from the modeling side, and I will explain later why it's important for me. And we came later on to testing, and then to the link from modeling to testing, who brought us to this model-based testing solution. Since we were focusing on the modeling side, you know, very early we worked with some big companies to try to verify the system. So the first one was with Untitled focused on model checking. Yesterday I presented the one with Thales focused on property verification, and we started this lab last year. So now we have our first, let's say, integration, first results, first product, I would say, available to do model-based testing. So first, to do model-based testing, we need a model. And I think it's key to model-based testing. The model must be quite good. It must be verifiable. So the idea here is to take a modeling language that can be executed and verified to make sure the model is right. Because it will be a reference. You will generate test cases out of it automatically. You probably won't look at the test cases, you know, one by one. You will just execute them. So you better be sure the model is right. So for that, we use SDL, Specification and Description Language from ITU. Do you know SDL? Who knows SDL here? Half of you? So it's a standard language from ITU, and mostly used by, well, has been used a lot by ETSI to specify telecommunication protocols, for example. And the point was to make the specification unambiguous, you know, so that implementations by different telecom manufacturers will be compatible with each other, which worked quite well. So SDL is modeling language, graphical modeling language, with an action language inside to make it executable. And that's very important. That's why I'm insisting on this. So as soon as the model with SDL is executable, we can use tools to simulate it and verify it conforms to what you expect. Okay? So I'm showing here an example of what we can do. And verify the model is correct. I'm really insisting on this. The model must be correct. You can also verify, that's the old presentation. You don't have the new one, Stefan, but that's okay. Of course, be sure that you have tried all possible transitions in the system. So I said in the beginning, we came from the modeling side, so we were working with SDL and with all these tools for simulation and cogeneration from SDL, and then we went to testing, and we thought, what would be a good testing language? And at the time, there was, actually, I think only one available, which was TTCN3, but it was the perfect fit because it has the same abstraction level as SDL, has the same basic services, you know, like timers, sending messages, and things like that. So it was like a good fit for testing SDL system. So we implemented also this TTCN testing language. And we started, you know, thinking, you know, how can we make a link from one to the other? So the first easy thing to do was that SDL can be executed, can be simulated. Well, TTCN3 can be executed and simulated as well. So what we could do is here have a simulation of the specification against simulation of the test very early in the development process. Okay? And from the specification, you further refine and maybe generate code out of it, but you could do the same from testing and run it on a tester. So that's what we did. And then we worked on how could we go further in the analysis of the model. And I mean, this is complicated. Huh? This is a complicated story, so we relied on third-party partners and mainly research labs. In summary, there are two main techniques to verify a model. The first one is to do exhaustive simulation, that basically is trying all the inputs in the system, all possible cases, and each time you run a case, you maybe verify a property. Okay? The other solution is symbolic resolution. With that approach, your system is basically a big equation you're trying to solve. So you take your system, the property with it, and try to solve it. So the complexity is different. It does not address the same type of systems. The first trials we have made with exhaustive simulation, we made a partnership with Verima, which is a lab in Grenoble. The conclusion was that on a real system, that generates too many cases. So that doesn't really work on a real system. Okay? That's why we started this lab with the CEA List to try the symbolic resolution and see if the results are better. So within that PragmaList lab, the idea is to, as I said, design a reference model that will be used to generate test cases. I think the batteries are dead here. So in order to generate, you need test objectives. The simplest one is coverage. Yeah? Let's generate all the test cases that will cover all transitions in the model. So that's simple. You don't have anything to configure. So that's the first thing we worked on is coverage. So it's very automatic. Of course, you can also set different test objectives. For example, you can target transitions, or you can define a property and target this property. But let's stick to this one, which is the simplest one for everyone. What we had to do to work with the CEA is to take the SDL model and export it to their internal language, whatever it is, so that they can read it, and then make sure that their tool has the same semantic of execution as SDL. Then they can run the stuff. You don't understand what they do, but and then in the end, you get a bunch of TTCN3 test cases that you can run against, against the implementation, not against the reference model, of course. So, from a tool point of view, the idea was to clearly separate both, so that if you have an evolution of the CEA tool called diversity, you can change it and keep the same version of SDL or the other way around. Okay? As I said, we have different types of targets. The simplest one is code coverage. And for that feature, it not only generates all the test cases that will cover all the transitions, but it reduces the number of test cases. So it's like the minimum number of test cases that will cover all transitions. With the few examples we had, it's quite efficient to do that. We also had a use case that wanted to target a transition, so we did that. Trying to make it easy, just graphically said, this is my target, please generate a test case that will hit the target. Don't try to, you don't have to deal with equations or anything like that. Huh? But when it comes to probability on observers, today it's still a bit tricky. You have to write this CEA language, and you have the property with this. So for the time being, there's no, let's say, nice GUI for that, but it will come. I cannot make a demonstration. I was not allowed to, so I'll make a PowerPoint demonstration. And the example here is an access control. So it's a system, where that is standing by your door. You slide your card in, and you type in your code. So actually, that creates quite a number of possible scenarios, because the number of possible cards or the number of codes you can type in generates a huge number of possible cases. Okay? So exhaustive simulation is pretty bad with this type of system, because if you have a 3-digit code, for example, and maybe 100,000 million possible cards, it generates millions of cases, which are most of the time useless. With this technology, it's easy to have an equation, so it's much simpler. And actually, within 10 seconds, you can find all the possible scenarios to cover all those issues. And it's not always 10 seconds. Huh? You know, this type of technology can take hours. So we made this graph that evolves during the exploration, so that you can see where you are, how deep you are in the resolution, the width, and how many transitions you have covered so far. And when it's done, you get the test cases. So for the sake of the demonstration, you can take the test cases and run them against the reference model to make sure it works, and that you cover 100%, and that works. Now the interesting thing is to measure that against exhaustive simulation. Here are a few figures coming from an exhaustive simulation tool on that same system. But to be able to run this exhaustive simulation tool, we had to reduce the system. So for example, the number of cards available would be only 2 cards. Okay? The number of digits you can type is only 0 and 1. 3 digits, but only a combination of 0 and 1, like a binary code. Huh? And if you do that, so restrict the number of cards and the digit range, you come down to 13 seconds. Okay? But it's very restricted. So that's about the time you get with this symbolic resolution. So it's even more efficient than with a very good restriction of an exhaustive simulation tool. And of course, the exhaustive simulation tool, if you let the card range or the digit range grow, that's the number of seconds you get with only 3-digit range and 4 possible cards. You know? So that's, as you can see, exploding. So we believe this symbolic resolution tool will be quite efficient in a model-based testing approach. What we are doing now is that we are, looking for use cases, because this is very new. We don't have any real success stories to show, only examples. So we are working with Alstom and SNCF and Airbus on this. But any people interested to check it out on the civil system are very welcome to contact me. So as a conclusion, what we try to do with that lab is to have an integrated toolchain. So you do your model and you get the resulting test cases within the same tool. Let's say the research technology is hidden as much as we can in the background. So you stick to your high-level models and high-level test cases. Also, the model is not dedicated to test cases. It could be a model that is used for specification and even design, if you want. It doesn't have to be on the right branch of the V cycle. And as I showed with these measurements, we have an efficient symbolic kernel that reduces the number of test cases. And that's also another thing that is not in the table I showed, is that the number of test cases is very small with the symbolic resolution tool, where it was very high with the other tool, the exhaustive simulation tool. And if it comes to a real system, we know things are complicated. This was a very simple example. So it has to be efficient, we know that. So it has to be very efficient on an example system so that it has a chance to be usable on a real system. I'm done, I think. Did you have any questions?
Yes, so quick question. Yes, well, talking to Marat, I mean, you have been mentioning here that this is done in a lab. Is there any way that people can somehow join this activity? And let's say I'm not using STL, but another tool. Is there any way that, or in other any places to kind of work collaboratively?
Or you can work with the CEA, they will be very happy to work with you, but it won't be part of the lab. The lab is PragmaDev and CEA List, so it's not within that technology I have presented. You will probably have to set something else with them. What they do actually, they do work with some other companies and use cases, other aspects.
I have a number of questions here. First one would be, I mean, I'm familiar with SDL and UML, so the obvious question that rises for me is, what was the deciding factor there? Is this the action language of SDL?
Yeah.
Yeah? Okay.
Yeah, definitely.
Okay, okay. And one important point I wanted to make was thank you very much for pointing out that validation or verification of the model is very important before you go ahead with testing. But I didn't really understand how was the model actually verified or validated in the first place. Was it manually done or automated? Can you spend some words on that, please?
The reference model.
Yeah.
Yeah, the basic idea is that you run simulation on the model to see if it behaves properly.
So which means exhaustive simulation?
No, interactive simulation.
Interactive simulation. So done by a human?
Yeah.
Okay, so a human is validating the model?
Yeah,
Okay.
the reference model. Yeah. Well, a human has to be in the loop somehow.
Yeah. This is what was not clear for me, so whether
Yeah.
it's done...
Then the test is automatically generated.
Yeah, okay.
You don't have, well, you don't have to look at it.
Okay.
But for the model, yes, you have to interact with it and verify it's what you expect.
You also mentioned that you did exhaustive simulation, right? Which means providing, let's say, a number of inputs to the system and seeing how the system reacts.
Yeah.
So where do you have the oracle from?
The oracle.
Yeah, so we can check that it works correctly. Let's say I have
It's
8
just-
bits of input that or 8 numbers that I have to put in. So I can try I can try the different combinations, and I have 2 power 8. So what happens if I have 1,000 inputs? 2 power 1,000. So I need to know the outputs that I'm expecting, right? So
No, you're not testing. The model is your reference, so you're not testing the model. That's why I was insisting on the fact that the model must be tested before. Okay, the model is considered to be right. Okay? That's what you do in model-based testing. So then the exhaustive simulation will try all possible inputs and see what the possible outputs are and generate the test cases based on that. But the model is right. Okay? That's not what you're testing. What you're testing is the implementation of the models by maybe another team, a subcontractor, or
Thank you very much.
Okay, thank you, Emmanuel.